Thank you. So let me see if I managed to make it work. Okay, spoiler. If we can go back to the first slide. Thank you. Thanks, I'm Christiana Spingola. I'm a staff astronomer at the INAF Institute for Radio Astronomy. Before starting, I would like to thank the organizers for giving me the opportunity to be the last talk of the conference and to talk about spatially resolved studies of cold molecular gas at high redshift by using strong gravitational lensing. So this work has been part of the strong lensing at high angular resolution program, SHARP, and here there are all the collaborators who made these results possible. So I will just give a brief introduction about the importance of the cold molecular gas, which has already been said several times during this week. It is a key ingredient because it's the fuel for both star formation and the aging activity. So we really need it in order to reproduce what we observe now in our theoretical framework. So you can see here a state-of-the-art hydrodynamical simulation from the Lastris collaboration that is color-coded by the gas temperature, as indicated in the top right. So you can see that, you could see that at the center of the most massive halos, there were explosions happening, and this is because of the presence of AGN. So the most massive halos sits in the intersection of the filaments where there is gas. So AGN feedback is really needed to explain what we observe in galaxies. However, we do not really understand it very well. And in particular, sometimes AGN show jets, and the role of the jets is super controversial because it shows both negative and positive feedback. So ideally, what we would like to do is to spatially resolve the emission from the AGN jets and that of the cold molecular gas in order to image directly their effect in the surrounding medium on sub-galactic scales. But at high redshift, this is really observationally under constraint, and this is because the CO120, which is the best tracer for the H2, is actually at very low surface brightness. So here in this slide, you can see on the left what we can obtain in the local universe in the beautiful M51, where we can detect, we can not only detect the CO120, but we can see all the substructure related to the cold molecular gas emission. However, when we go at high redshift, the situation is a little bit different. Here you see recent results from Castillo et al. 2023, where we have galaxies at redshift larger than 2. The detection of the CO120 is super robust because of the increased sensitivity, because of the increased bandwidth of the JVLA high frequency part, but the spatially resolved studies here are much more challenging. So the ngVLA will be a game changer in this kind of studies because it will have the sensitivity and the frequency coverage to trace several CO transitions and especially the low J transition of the CO across the cosmic time. So here you see a simulation from Casey et al. 2018, so showing a starbus galaxy at redshift larger than 4, and this is what we will observe with the ngVLA. So we will be able to get that substructure in the emission of the CO120 on kiloparsec scales also at these cosmological distances. But before the ngVLA comes online, we can use galaxies as cosmic telescopes in order to get that enhanced sensitivity that we need to detect the low surface brightness emission of the cold molecular gas. Just to be on the same page, this video shows how strong gravitational lensing works. So we have a background radio source, in this case jetted AGN, whose emission is deflected into multiple images and magnified by the presence of a foreground galaxy that we call lens. So the gravitational potential due to this object basically deflects the light, it amplifies and magnifies the background source, in this case, into gravitational arcs. So we have a distorted view of the background sources that otherwise would not be possible to detect or to spatially resolve with current instruments. So strong gravitational lensing is a very powerful cosmological probe because we can get information on the lensing objects and therefore trace the dark matter and baryonic matter distribution and content across the cosmic time, but it also gives us this high spatial resolution and sensitivity view on the most distant galaxies. And in this talk, I will focus on the source plane. So we typically use the magnification factor in order to indicate how much the source is magnified because of the lensing effect, and that is the ratio between the lensed image area and the source area. So the higher the magnification factor, the better, in order to study, for instance, the low surface brightness emission of the cold molecular gas, but also the smallest AGN jets that can be at high redshift. And this is what we have done for these two systems that show very high magnification factor at the radio wavelengths with magnification factors larger than 40. And here you see MGO751, which is my favorite system on the left. The background source is at redshift 3.2. And on the right, you can see JVAS B1938, where the background source is at redshift 2. So in the green contours, you are looking at the moment zero map of the CO120 distorted by the lensing effect. So this is a distorted view of the background source. But you can also see that here we have a very rich data set. So other than the JVLA observations that are detecting the CO120 in the two systems, we also have Keck adaptive optics, several HST filters, and radio continuum observations in the case of 0751 with global VLBI, while in the case of B1938, those are B-array observations at 37.7 gigahertz. So this rich data set is not only important to have a comprehensive view of the background source, but also to model the gravitational potential of the lensing object. This is the price that we have to pay in order to get the source properties. Namely, we have to model the gravitational potential of the lensing galaxies, which in these two figures, in these two images, are shown in the center. So these rich data sets give us a high precision on the lens mass modeling, and when we de-lens the emission, this is what we may get. So we use a pixelated source reconstruction, which is a state-of-the-art lens modeling software developed by Simona Vegetti at MPA, which for the radio data fits directly the visibilities. And so starting from the left, we have the moment zero map, an intrinsic property of this galaxy at redshift 3.2, where we can find this extended molecular gas reservoir and massive with masses of about 10 to the 11 solar masses on several tens of kiloparsec scales. The moment zero map shows a peak that is offset with respect to the radio emission, which is shown here in black contours with these very small radio jets. This might be an indication of AGN feedback, but it could also be that we are looking at an offset star formation here. So if we zoom in around the AGN jets, here the Keck adaptive optics and HST data become very important because we detect two separate optical companions, one that is extremely compact, likely a proto-bulge, and another bluer companion traced by the HST. And so we are maybe looking at interacting galaxy, and this is further supported by the velocity fields on the right, which show two separate gradients, so complex velocity fields, which are an indication for merger galaxies. In the other system, now we are looking again at the intrinsic properties, and just please take a look at the scale. So we are able to go to the sub-galactic scales, which will be possible to do that with the ngVLA without the lensing effect. And the system is a little bit different with respect to the other one. We have still a very compact stellar core, which is hosting a compact symmetric object where the white contours are the hotspots. And we have an elongated cold molecular gas reservoir with a gradient, and now we move on the right for the velocity fields. So this gradient along the major axis is typical of rotating disks. And so also the CO120 spectrum, which is shown on the right, shows this double horn profile, which is typical of rotating these galaxies. The different amplitude of the horns of the CO120 spectrum is just due to the differential magnification. So of course, we will need kinematical modeling to confirm the nature and assess the origin of these velocity gradients. But if we put these two systems together with the other pixelated reconstructed lensed sources, showing also jetted AGN with low J transitions of the CO, this is what we get. So we have two main populations, which are disks on the left, order rotations on kiloparsec scales, compact systems with gradients with order rotations on the major axis. But we also have mergers, namely complex velocity fields on much larger scales, and so much more extended molecular gas reservoir, which is what we expect from our theoretical understanding from our simulations. So there also seems to be that the mergers are at higher redshift with respect to the disks, but of course here we have only 6 sources, so we cannot really conclude anything in a stringent way. We will need many more systems. So we are trying to expand the sample by looking at other 2 systems. Here it's the CO120 moment zero map from the JVLA for a background source at redshift 2.32 and the other at 3.93, so stay tuned for the reconstruction of these systems. Of course, these 2 will not be enough. We need a statistically significant sample, and we started to search for lensing systems at the radio wavelengths because we want to test the occurrence of AGN jets in cold molecular gas reservoirs in a wide field VLBI survey, which is the MGIVE20 survey, which is a survey with a VLBA at 1.4 GHz from Deller and Middelberg 2014. And so by using lensing arguments, so very simple selection criteria, we rediscovered the 2 known lensing systems, which was a proof that the method actually worked, and 2 final lens candidates that are shown on the right, which we followed up at higher sensitivity in order to confirm their nature. So this kind of method can be applied in the future survey with the SKA1MIT, which is predicted to unveil 10 to the 5 strong gravitational lensing system. So this sample will be revolutionary for all the science cases with strong gravitational lensing, because we will be able to properly assess the mass density profile of lensing galaxies and better understanding the high redshift universe and the background sources with a sample like this. So here, on the left, I'm showing an incomplete comparison of angular resolution as a function of frequency for some of the current and future VLBI arrays, such as KA and ngVLA plus long baselines. And on the right, the surface brightness sensitivity as a function of frequency. And this is the important part for detecting the low jet transitions of the CO, because the SKA and the ngVLA will have the sensitivity necessary to detect this at high significance. And the ngVLA, as it has been already said, it will have the frequency coverage to cover the low jet transitions across the cosmic time for the unlensed population too. But we can still combine this instrument with strong gravitational lensing, and we can get even enhanced spatial resolution and sensitivity if we have the strong lensing effect on top of these observations. And this is what is shown here in red and orange. So we can even go an order of magnitude deeper for a typical quadruply imaged lensing system with a magnification factor of 15. However, I hope that I convinced you before that we really need complementary multi-wavelength observations if we want to have a comprehensive view on the background sources, on the origin of velocity fields, for instance, and understanding how often mergers occur, where the AGN jets are located with respect to the center of the galaxy, or how the cold molecular gas is distributed. So we will, with respect to the host galaxy. And so we will need matched scale areas with optical and near-infrared future surveys if we want to have this view, but those are also necessary to have a very good understanding of the gravitational potential and to find lenses efficiently, because the radio alone is efficient, but it has been demonstrated that if we use multi-band observations, we can really get faster results for finding lensing systems. And so we will also need the VLBI capability of both the ngVLA and the SKA if we want to spatially resolve the lensed images. And spatially resolving the lensed images meaning spatially resolving the background source. So I will conclude now, leaving my summary, and thanks a lot for your attention.
All right, thanks. We'll get started with questions. Go ahead.
High redshifts, one would expect CO1 to 0 will start to be depopulated, and it'd be better to look at a higher 2 to 1 or even higher. It's surprising in a way that at redshifts 3 or so, you're still getting strong detections at 1 to 0. I just wonder what your comment is on what the higher transitions should be at those redshifts.
So we haven't looked at observations at higher transitions, but the higher transition of the CO should probe much more compact regions. For instance, that was what I was showing at the beginning with the simulation of the starburst galaxy at threshold larger than 4. So they are probing kind of different regions of the cold molecular gas. So they must be much more compact with respect to the CO120. But indeed, I guess that would be a really interesting follow-up for these systems to understand what's going on at the other transitions.
Okay, there's a question right there.
Hi, yes, thanks for this very nice talk. In the same vein, perhaps, but I was wondering about the depletion times or star formation efficiencies for these sources. Have you looked at those? I was curious, you know, when you take the ratio of the star formation rate and the molecular gas mass, what you find.
So we started to look at that. However, the uncertainties that we got were really large. So on top of my head, I don't have the numbers, but we can look at this later. I remember that we got very, very large uncertainties, and so it wasn't very, stringent value to put in this work. Thank you.
Okay, in the back.
This isn't really a question for you, but maybe for Eric or somebody. What about weak lensing in the radio? Has there been progress with SKA pathfinders or better forecasts for?
So I don't do weak lensing,
No,
but
I
if there is
understand.
anybody here, I guess they can take this question.
We can, so perhaps we can continue that discussion on Slack. Any other science questions for the speaker? I have a quick question, actually. Do you have any IFU data or any constraints on the ionized gas conditions in your high redshift lensed radio galaxies with CO?
Yes, we do. We have Muse observations for the systems, for a few of these systems, and we're really trying to get down of them because the spectra are extremely complex. And so that's, I guess that once we fully understand the ionized gas and why it's so complex with several absorptions along the emission lines, so that would be really interesting to put everything together. And so, yeah, thank you. But that's our next step.
All right, any other questions?
Hi, thanks. This was a very great talk. I was wondering, like, are these images like detailed enough to say something about the filamentary structure? So do you see, if you would take a power spectrum, would you see the same scales as in the local universe, or is it not as filamentary?
That's complicated because it's also about our limitation in reconstructing the source area from the lens modeling perspective. So you mean on scales larger than tens of kiloparsecs, right? So we are sensitive to a certain source area, and so it really depends on the lensing configuration, so the alignments between the source and the lens. I guess for some of these sources it could be done, for instance 0751, which shows this triangular shape, right, that it resembles kind of filamentary structure. I guess the ngVLA observations for this system would be quite nice to test that.
Great, thanks. Looking forward to that.
All right, any other questions? I have one last quick question, actually. You mentioned multi-wavelength synergy and you highlighted Euclid. I'm just curious, I know off the top of my head, I think Roman would be an amazing complement to ngVLA and SK with its HST-like resolution for the whole sky. What are some other really important facilities that you envision for strong lensing in the future? Well,
let's say for single targeted like objects, I guess JWST can already give us the counterpart of the KKO that we saw, but in much less time because of the sensitivity. Yeah, I guess Roman and Euclid will be the best chance. I guess one thing that we should really look at, and I didn't mention that, it's the temporal behavior of these systems. So something like the LSST would be also very interesting to understand how the system varies. But the angular resolution here is playing a role, so we really need to be careful about that. But that would be an interesting part.
Thank you so much.
Thank you.
All right, let's thank our speaker again.
Thanks.